or so in Berkeley, gas meters have finally become computational, so someone doesn't have to go from house to house to read the gas meter. That was something he was talking about in 1832, that machines should be able to do this. And then finally, the question that we came to, the calculation of logarithms. Well, I guess that as you didn't, there's another piece that has been snipped out by this so-called computer. That as you didn't read the book, I can't quiz you on whether you understood what he was talking about with the difference engine. The difference engine was a very canny device. That was actually a little piece of it that was rebuilt later. He had enormous trouble with getting funding for building his machines. He took a lot of money from the government. It was always more expensive and took longer than he predicted. He never got to build the machines he wanted, and halfway through, he actually changed the type of machine he wanted to build, and the government thought he was kind of playing fast and loose with them. But his first idea was to calculate any function, any mathematical function. If you can break it down from a multiplication into an addition, then you can have a machine that can simply do it by, if you say you have to keep on adding the unit 2, then it just has to turn 2 notches. And as one spindle turns finally through 10 notches, it'll turn the next spindle if you're built in units of 10. So if you can make any problem an additional problem rather than a multiplication problem, you can build this machine that will actually be able to calculate those additions, however long and complex they are, and that would produce your logarithm. And so what he discovered is if you have a function like fx is x squared plus 4, and so here is x, you can start to calculate these solutions simply by breaking down the problem into differences. You calculate the first 3 or 4, and he noticed that if you say, well, okay, fx squared plus 4 for 1 is 5, for 2 is 8, for 3 is 13, if you calculate the differences, they become 3 between 5 and 8, 5 between 13, between 8 and 13. But the next layer of differences, if you then calculate the differences between those, they're all 2, absolutely uniform. So you can turn this rather complex task simply into a process of adding 2s. You want to at least take that on faith, if not consciously with me on that? If you sit and look at this, you will see, and in fact, if you read his explanation, you will find it even better. So he said, here's a complex mathematical formulation. So instead of having to work out what fx squared plus 4 is if x equals 3, you have the first 2 answers for x equals 1 and 2. You add the 2 to the 3 and you get 5. You add the 5 to the 8 and you get 13. It becomes a series of additions. And in the end, the only additions you have to make are 2s down the line. All right? So he worked that out and said, well, if you can do that, then you can have a machine that will do it for you. And so that was the difference engine. And there, in many ways, although it was actually forgotten for the most part for a long time, is our prototype of computing. And Babbage is the person who we can turn to that, just as we turn to Gutenberg in some ways for print. In fact, we turn to him so significantly that opening in London, actually today, I think, no, on the 29th of March, is an exhibition of Babbage's brain, which you can actually see up in the top corner there. Not only Babbage, I think Einstein's is there, an exhibition of brains, the mind, does matter. So, but that's a picture of Babbage's, if you wanted to know. Let's move hurriedly along. Okay, he realized, though, that was kind of a limitation. And so while he never got the machine built and got into fights with the engineers trying to build it and got into fights with the government who saw it was a good idea and were trying to fund it, halfway through he decided that really a difference engine was a very boring thing to try to work with. And so what he was going to try to do was build the analytical engine. And that's where we come even closer to what we now have in front of us today. Because the idea was that it would be programmable. That you could, instead of just being able to do one task, you could actually make it do a series of different tasks. That it would be able to store numbers as it was calculating them. So you wouldn't simply just get an end result, but you could go back and use that result and recalculate with it. That you could have loops and branching and all the sort of functions that we expect when we write code now. He again started to try to build this, a much more complex engine, clearly, than the differential engine. In some ways what he did, rather than build it, was really scope it out. But far enough that it's an impressive deduction. People, in fact, have since built modules of it and persuaded themselves that it probably would have worked. 2 of the sources here, one is, which Jeff has already mentioned, I think, in terms of the printing press, very influential, is the Jacquard loom. And Jacquard, who created the loom in France, decided what he really wanted for a loom was a loom that could weave all sorts of different patterns in the material. And if one day you were working on a particular pattern and someone came in and said, that pattern you were weaving last week, I'd really like to have some more of that cloth. To set up the machine to do that, Jacquard thought should be a simple task. A simple task if you could actually have these cards that would record how the machine should move to weave that particular pattern. So you would, if the change order came in, you take out the card that was running the machine, put in a separate card, and the machine would automatically start reprogram itself to produce another pattern. So Babbage, in going around the machinery of Europe, and particularly in France, saw this, thought, now that's what I want for that computer. And in fact, these are Babbage cards that he designed in some way to try to run this machine. He never, as I say, got it off the ground. He worked with an astonishing woman in many ways, astonishing but also different. She was that painful thing in the English, comes from aristocracy, and when you also marry into aristocracy, you end up with about 15 different names. So she's sometimes known as Ada Byron, Lady Lovelace, or just as Ada Byron, or just as Ada Lovelace. If you see those names, it's only one person, but she covered a lot of ground. But she, in some ways, is credited with understanding and indeed devising the kind of programming language in some ways that would run this machine. It was a machine, as she said, that not only would have foresight, but that could act on that foresight. It would know where it would want to go, and it could change its own pattern. It could regulate itself as to where it would go. I want to put in something about Bernoulli's number in one of my notes as an example of how an explicit function may be worked out by an engine without having been worked out by a human head and hand first. So it wasn't simply doing what we had told it to do, it was doing things that we in many ways couldn't do. And she saw the connection with Jacquard. Both of them are weaving in a way. One is weaving numbers, and the other is weaving material, but it's the same idea that if you can program it to do this pattern of weaving, it will go off and look after itself. One thing just to pause that, yes. Yeah, in fact, and on that previous slide, that's what those cards were. They had, and that was what, those were the Babbage cards, indeed. And they remain, again, just to show how Neanderthal I am. Not only did I grow with Napier logs, but my first computing was done with cards that look in many ways like Babbage cards. You had to walk around with this great stack of cards in your pocket, and that was your program. And it would do about 4 things, say 2 plus 3 times 9, a huge stack. And if you got it wrong, you had to go back and work out which card had the wrong hole in. But one more thing to say before we move on. In fact, into today's paper, there is a big thing about trying to get women into computation. Ada Lovelace was there from the start. And in fact, people like Adele Goldberg who produced Smalltalk. A lot of very significant women in the history of computation. But they keep getting written out by blather like this guy who thinks they're more important. But anyway, she set a precedent and one worth following. In relation to sort of what we have thought about over the past, she's interesting about how people talk about discoveries. And she says at one point, looking at this, what has happened is that first when a machine comes along, people tend to overrate it and say how remarkable it is and say it will change the whole world. And then they come along and they kind of undervalue it and they start to deprecate it. But then she says about the analytical engine, well, it had no pretension to do anything. So she actually sort of fulfills her own prophecy by underrating what it could do. As I say, Babbage never actually finished the analytical engine. The difference engines were produced. People got the idea, thought it was very interesting, and began to work on them. Though, in fact, if you read the Campbell-Kelly chapter that was set for this class, he talks about how in many ways, when they were working on difference engines in MIT in the 1920s, so people rediscovered Babbage, but had forgotten about him almost completely and his work. But there were some in Sweden, this father and son combination, the Schutzers, produced a difference engine for calculating, and had the very cool idea of putting a printer on the end of it, and therefore that you could actually get a printout of its results, and that would make life much cooler. And in fact, the nice story goes, the power of printers remains remarkable down at Xerox PARC when they were first working on the Ethernet, and they thought connecting computers together would be this really cool thing. But the guys working on the Ethernet, which we all rely on in different ways now, were to take it down and put it up and take it down, put it up. Nobody would notice whether the net was there. They just sit hacking on their machine, and they weren't really that connected. And one of them said, but one day they took the net down, and suddenly all these office doors opened, and people said, what the F is going on? And they couldn't think, why was anything different today? And then they realized that previous week they had first connected a printer to the end of the Ethernet, and nobody really wanted to connect to others' machines, but everybody was connecting into the printer, and it made a huge difference. So this was a sort of savvy moment when they thought, let's have a computer, a printer around here. The one came to the United States, was used in the observatory over here for different observatory calculations, and they were used a lot for, well, not a lot, but people began to use them for life insurance and the length of life calculations. There were also at the time, and this is something to remember, that as we work with digital computers, there was a long history also of analog computers that goes along with this, which come out of this work. Particularly, I won't go into this, Kelvin used them for predicting the tides, which became very important for different reasons. They were started to use for predicting the weather, and there was analog computers that did most of the work. Okay, so shifting right along here. Okay, so what was the demand side? So there was this idea for these machines. People saying they can do this. Well, somebody wanted better logarithms, okay, but that isn't a massive demand side, clearly. Others said, well, we can do actuarial calculations with them. But there is a sort of question which now doesn't seem as obvious to us, I think, about who would really want these machines. And Schütz, in fact, said that just one of these different, we would suffice for the whole world. You don't need more than one. It'll do all the calculations of this sort you ever need. One of the great underestimations of all time. And in fact, one that we'll meet again. People keep tending to see these things and think, they probably don't have much use. They'll be useful. But who wanted them? Well, the first real driver, and in fact, you see this with Babbage, it's where he got all his money from, was the government. And the government had multiple interests in them. We've talked about some of this. When we talked about science and the history of science, we talked about the bills of mortality, of registering the dead in order to be able to calculate whether inoculation was going to be successful or not, to know whether the plague was spreading through towns or cholera was coming. So government always had a huge interest. In fact, one of the great drivers, but not often thought of, the information society is the government. And through the 18th century, which we spent so much time on, I mentioned this before, I think the government was really one of the great drivers of what we now come to think of as the information society in numerous ways. In fact, you can see that it's very deeply embedded in our language in that word that we think of as so familiarly now, statistics, of course, comes from the same word as state. And for a long time, it was thought of that statistics were government information. Statistics was something to do with government. Comes up in Germany in the 17th century, but in fact, by the 18th century, it first appears really in the English language in this massive work by this rather odd guy, John Sinclair, just to try to write down every fact that he could about property and land ownership and employment in Scotland. And as you can see, it's called the Statistical Account of Scotland. And it's of Scotland as a state in some ways. And this is volume 21, I think it was 29 volumes or so. A massive account that attempts to register all the facts. And it is, and you see, Encyclopedia Britannica takes it up, and statistics comes into the language, in part by this kind of governmental information. And in that way, by the 19th century, this is the stuff that primarily involves the state. And again, you can sort of see some of this if you actually look. And I sometimes think of California as the first great statistical state in this way. These are extracts from the laws of California. But what's remarkable about them is how much of them is occupied with recording information or processing information. The very first law of this state is to set up a public archive, to store information of one sort or another. It's seen as almost the first thing the state has to do. The next is to establish a state printer, to produce and publish information about the state. Then there's pilots for San Francisco who have to produce charts for ships coming into the bay and regulate their passage. The controller, the treasurer, all of these are people, massing numbers, crunching numbers, one sort or another. And as you go on, so much, even noting a notary, a commissioner of deeds, the incorporation of city, it's all to do with recording and declaring this as definitive information. So the state, in some ways, becomes the great central nexus of information. And there, as you can see, through much of this, looking at weights and measures and regulating those, more information, down rather lowly in number 117 come we, the incorporation of colleges. But we're in there too, we're another information institution. So the way that you can read California in terms of the informational state, well, one of the massive tasks that the government took on, and America was a constitutional task, was the census and the recording of the number of people in the country. Again, now to us, it's kind of second nature. But for reasons I suggest was odd in one way or another. This is the 1850 census. There you can see the states more or less come in by order of precedence. So California's just come into the fold. So there it is. The territory's below it, so it gets its money. The population is relatively small if you look at it compared to some of the other states. But the census, in fact, is from the beginning of the country almost, this enormous national preoccupation. And some of you will have seen that it's still in some ways an enormous national preoccupation. They've just released the 1940 census numbers, and it crashed the census office. Everybody, for some reason, wanting to read about 1940 from Monday when these were put up, it's been almost impossible to get into the census office. These figures still have a fascination. In fact, even today's newspaper shows they have a fascination. Using old census records, they've managed to recalculate the number of people who died in the Civil War. And for such an extraordinary, aggressive and barbaric war, what's terrifying is they've underestimated the deaths, probably by around 20% if Gettysburg is anything to go by. That was in the news this morning. So the state starts to have these preoccupations with what starts to be very large and tricky to calculate and to collect numbers. In America, it's to do with the Constitution. In other places, less so. One of the odd things in Europe was that actually countries didn't know whether their population was growing or declining. They had no idea. England by 1800, enormously successful business state, had no idea which way its population was going. And there were lots of different arguments. In fact, it didn't know until the middle of the century whether it was larger or smaller than its greatest rival, France. Now, France was actually about 6 times bigger. But the idea that you want to keep going on, going to war with this country, and you have no idea whether it's the same size as you or not, it's wrong. And there were different arguments. Some saying, there was a biblical argument saying that we've been declining ever since the death of Christ. So numbers in the world must be falling. And nobody had any data of any sort to fight it. Or indeed, Malthus, who had predicted that we were going to suffer from overpopulation. But people dismissed his argument because they said, no, the population isn't growing. So it was a sort of open question. So one of the things that governments began to do is that we really need to find out. And there were all sorts of other reasons that they needed to find out. And they go back a long way. I mean, most of you will probably recognize the piece of text on the right here. It came to pass in those days that there went out a decree from Caesar Augustus that the world should be taxed, and Joseph went up from Galilee out of the city of Nazareth, etc., etc. Why were, in the biblical story, these two people, one heavily pregnant woman in a stable in Bethlehem on that particularly significant day? Well, because they were going up to sign up for the tax register, and they had to go back to their particular town to sign in. So governments collecting tax numbers have always been a prime goal of government collection of statistics, to know who to tax. The military, too, to know who will serve in your military. You have to have registers of that, how many men between the ages of 16 and 35 in every town, so that you can call them up. How many people live in that town, how should they be taxed? Again, in today's paper, we see that the Irish are rebelling against the property tax. One of the great chases you see is the government trying to work out who it can tax, and the population trying to work out how they can avoid being in those registers and being taxed. Some of you perhaps who've been to London will have seen houses that look like that, particularly bleak-looking houses. Anyone know why you see houses that look like that? There was a window tax. It was one of the easiest things in the world to say, we'll just tax houses by the numbers of windows. The rich will tend to have more windows than the poor. You don't have to get anybody to sign up. We just go by and write down how many windows are in your house. But the people weren't that stupid. So they just began to brick up their windows and say, I can do without windows, I won't have to pay the tax. And you still see some houses with that around London. So government is one of the major interests driving all this. Business is another. As businesses grow, as they become more complex, how they can coordinate all the figures, all the data that they have to deal with. One of the passages, a nice passage in Babbage, which he gets, he's wonderful. He looks at something like the steam governor, and he does spend pages and pages describing this thing. It fascinates him so much. So he sort of does this with, clearly what the business people of the day was a fairly standard notion of how you coordinated activity. There were numerous banks across London, and people would come into a bank and they would write a check on Bank B where their money was and ask Bank A if it would cash the check. And with certain arrangements, a lot would. And so Bank A would end up with a lot of Bank B's checks, Bank B with a lot of Bank C's checks. Everybody would have checks owing to them and owed to other people. And so they came up with the idea, the word is still used, of the clearinghouse, and it fascinated Babbage, where you had a long series of desks with people sitting behind them to represent each bank. And then you had a lot of people coming in with the checks from each bank, and they would walk around slowly in a circle, and as they looked, well, here I've got the checks for Dugit's Bank, and there's Dugit's Bank, so I'll put it in that slot here, and then here's the check for Nunberg's Bank, I'll put it in Nunberg's Bank, here's Blake's Bank, and so you would deposit all the checks out, and they would make a note of them, and then you would walk around a second time to where all the checks for your bank were, and you would pick up all the checks that other people had dropped off for you. You'd do a very quick calculation to say, how much have I dropped off, how much have I picked up, and the difference was often only a few pounds. And so instead of you having to pay out thousands of pounds for the checks you owed and take in thousands of pounds for the checks that owed you, by going through a very simple clearing system, it was very efficiently organized so the amount of money that needed to change hands was really quite slight, while the amount that was actually being calculated were huge amounts of money in the system. But Babbage saw in that, and was right to, a kind of computational system for allocating priorities. So there you can see business starting to say, well, what if we could do this in a machine? And we end up with the modern clearinghouse. All sorts of technology then is moving into the business world, some of which we would think of computational and some not. Jeff, I think, already talked about carbon paper, the amount of copying of documents that had to be done, again, something we think that computers will do now, with a whole separate set of functions. We begin with carbon paper, we move up to the typewriter, and Remington, who produces the typewriter, the calculator, Burroughs produces the calculator, and we start to see in small versions what Babbage had been working on to be able to add and multiply numbers on the desktop. One of the most significant in many ways from NCR, the National Cash Register Company in Dayton, is the cash register. And again, you'll see the term that Babbage used, the register being used. The cash register, why was the cash register invented, do you think? Yeah. Yeah, I mean, that's exactly the right answer. In fact, so many people think, well, it's how to add up the numbers or to calculate change. But Adam said, absolutely right. No, it wasn't. It was to keep track on employees and making sure employees weren't putting money into their pockets as money came over the counter. So the little figure would ring up and show both the client and the shop assistant how much money was going in the till, and it would calculate, therefore, how much would be there at the end of the day. So all these machines in different kinds of computation were moving into business, and business was starting to be taken over by first people and then machines doing these jobs. And so you start to get businesses become filled with what we now have as a classification of information workers, people who, the clerks, as I would say, or clerks, as you would say. You can see the growth in the clerks is enormous. More significant is the growth in the number of women going into these jobs. And in fact, the novels of the turn of the century are full of accounts of women now in these new jobs. So by 1921, and this is in the UK, women have suddenly turned the profession more into a woman's profession than what it had been a man's profession. And you get the notion of what became called the typewriter girls. And as you can see, I hope from this, this passage from Frank Norris. Anybody here read The Octopus? Shame on you. One of the great novels of California corruption. If you want to know about the corruption of the railways in California, it's a wonderful novel. It's a great novel. But just one of the chapters ends up with the most horrifying death. One of the great horrifying deaths. I won't tell you how it comes about up in the bay here, loading grain ships on the bay. But just one of the chapters happens to open with in his office in San Francisco, seated before a massive desk of polished redwood, very ornate. Lyman Derrick sat dictating letters to his typewriter. Well, it wasn't because they had an automated dictation system. It was because typewriter there was a woman, was someone sitting down. So again, as with computer, these were first roles played by women, and then that were moved in. Well, not necessarily women moved into machines.